Hello everyone, my name is Ali Pakinat and I'm a postdoc at the Institute for Robotics and Intelligent Machines working with Panos. One of the projects I work on here is the steering of the state of stochastic hybrid systems. An illustrative example of these types of problems is the multi-stage landing of the booster of Falcon 9, which at separation is traveling at around 8,000 kilometers per hour, and throughout multiple stages of operation, it is required to come to full stop at the exact location of the landing platform. Within each stage of the operation, the booster is exposed to stochastic uncertainties, thus is governed by stochastic differential equations of this form, and the transition between these stages are either autonomous switchings, such as the entry into atmosphere, which requires some functions of the state to hold in order for the transition to occur, or these conditions are controlled, meaning that they are entirely up to the controller to decide, such as the activation of burners. The conventional approach to obtain the desired terminal state requirements is to look at the total expectation of the state and its covariance and to enforce equality and inequality constraints over the distributions of the terminal state. While these methods are powerful and efficient for linear and non-hybrid problems, their extension to nonlinear systems and stochastic hybrid systems are not straightforward, since the majority of the discussions center around Gaussian distributions for the densities, which are no longer guaranteed to hold in the presence of nonlinearities and switchings. In contrast, we realized that by looking at the expectation of the terminal state, given the information available at all intermediate times, we are able to successfully achieve the steering goal. We derive the necessary optimality conditions in the form of the terminally constrained stochastic hybrid minimum principle, which declares the optimal continuous input as the minimizer of a family of system Hamiltonians whose evaluation not only requires the solution to the forward process in the system, but also on the adjoint process, which is governed by a family of backward stochastic differential equations. In other words, the adjoint process is the unique causal solution to this backward stochastic differential equation with this terminal condition and these boundary conditions relating the value of the adjoint process before the switching to its value after the switching. Notice that if switchings are autonomous, which means that the time of the switching is determined by the satisfaction of these switching manifold conditions, then this unknown parameter, scalar parameter P, is determined by this Hamiltonian continuity condition, and if switchings are controlled, then this term no longer appears, but the unknown switching time, the optimal switching time, is determined by this Hamiltonian continuity condition. While we are working on the solution of these forward-backward stochastic differential equations in their general nonlinear form, for the special case of linear stochastic hybrid systems with controlled switchings, we have been able to provide analytic expressions for the solutions in terms of state transition matrices, controllability gradients, and Riccati matrices. As you can see in this numerical illustration, the optimal switching time is not a deterministically identifiable variable, but indeed it's a random variable adapted to the information obtained from realizations of stochastic uncertainties in the system. Indeed, this form of optimal switching time identification is only possible because in our formulation, the terminal state constraints are updated according to the realizations of the uncertainties in the system. Thank you very much for your attention. I will be happy to answer your questions.
Hi, this is Zhang. I'm going to talk about our work, consensus algorithm for opinion dynamics on the sphere. Here, we're considering a special interaction graph, which is unsigned. The opinion state can be modeled by unit length vectors Vi. With control input Ui, the opinion dynamics on the sphere can be described by equation 1. The problem we are going to solve is to design the control input UI to achieve stable dissensus equilibrium. We are using the Oja PCA flow to model the opinion dynamics under both constant covariance H in equation 2 and the variant covariance CV in equation 3. The goal here is to study the behavior of the two types of Oja PCA opinion dynamics, and we also want to analyze the stability of consensus and dissensus equilibrium. For constant H, we denote Q to be the unit length eigenvector corresponding to the largest eigenvalue. For opinion state Vi, random Vi is converging to Q, negative Q, or remains unchanged. It depends on the initial inner product between Q and Vi. The two examples here show that the opinion states can convert to stable dissensus or stable consensus. This means that the constant H cannot give us a reliable dissensus algorithm. And this is why we are considering the variance covariance matrix. The opinion dynamics using the variance covariance matrix can give us unstable consensus equilibrium. With perturbation, the opinion state will not convert back to consensus. Instead, it will convert to dissensus. The linearization matrix AI, it is strictly negative definite at the dissensus equilibrium. And this led to, under the PC dynamics, the dissensus equilibrium is locally asymptotically stable. Starting from non-equilibrium state, the opinion state will convert to the dissensus equilibrium. And lastly, the simulation of 20 agents converging to dissensus equilibrium also showed that our algorithm works for larger groups of agents. So that's the end of the presentation. Thank you.
Hello, my name is Mariah Schrum, and I will be presenting on my project, Improving Robot-Centric Learning from Demonstration via Personalized Embeddings. I'm advised by Dr. Matthew Gambale and Dr. Sonia Shurnova.
The current state of the art for learning from demonstration is dataset aggregation, or DAGGER. DAGGER requires the user to demonstrate the task a set number of times. The agent then rolls out a policy learned from the user demonstrations. During policy rollout, the user must provide feedback to the agent. The new labels, i.e. the feedback provided by the user, are aggregated with the previous demonstrations, and the agent is retrained on this new dataset. This continues iteratively until the agent has learned a good policy. While this algorithm works well if the labels provided by the human are high quality, prior work has shown that humans often provide poor labels that may be time delayed or over or under corrected. We want to see if we can learn a mapping from poor human labels to better ground truth labels to improve upon the performance of DAGGER. In this work, we are motivated by the assumption that humans exhibit various and distinct styles when providing corrective labels to the learner. Some demonstrators may overcorrect while others may undercorrect or give delayed feedback. To accurately map a demonstrator's label to a label closer to ground truth, we must first learn the style of the demonstrator. Here we see our network architecture, which simultaneously learns the style of the demonstrator via personalized embedding W, and learns the mapping from demonstrator label L sub tau to the difference between the demonstrator label and the ground truth. We create artificial demonstrator data to test our model architecture. We train our model on 4 baseline tasks with 5 DAGGER rollouts per task and 40 artificial demonstrators. We find that we are able to improve the corrective labels by 61% on the calibration training tasks and 55% on the holdout test tasks. On the left is a plot of the learned embeddings. Because similar demonstrators tend to cluster together, we can conclude that our embeddings learn a meaningful representation of an individual's demonstration style. Next, we conduct a human subject study using the AirSim car domain and an Xbox steering wheel. We first collect a set of training participants who will perform a set of calibration tasks used to train our model. We then plan to collect a set of test subjects who will complete the calibration tasks, and then each subject will experience our novel algorithm, Dagger, and supervised behavioral cloning. We will compare the quality of our algorithm's policy and the workload to the baseline Dagger and behavioral cloning conditions.
Thus far, we have run 10 training subjects on the calibration task. After training our algorithm on the subjects, we were able to improve their labels by 70%. Our next step is to run testing participants and compare our algorithm to Dagger and behavioral cloning.
Hello, my name is Nick Marios Kokolakis, and the topic of my presentation is bounded rational unmanned aerial vehicle coordination for target tracking. This is joint work with Professor Kyriakos Vamvoudakis. First, we will start with the problem formulation. We consider that NUAVs are tasked to pursue an evading target. All vehicles are modeled as Dubin's vehicles, flying at a constant altitude and at a constant airspeed. In fact, in a target tracking problem, we are interested in the relative motion between the UAV and the target. Therefore, by working in the polar coordinates, one can readily derive the tracking dynamics for each UAV. Finally, one can obtain the ensemble dynamics by defining the augmented state vector. In the sequel, we shall define the performance index. This guy allows distance coordination, whereas the player's input penalty functions are non-quadratic so that they enforce bounded input signals. Finally, note that the team of UAVs attempts to minimize J, while the target tries to maximize it. Depending on the cognitive capabilities of the agents, we shall consider two scenarios. The first one concerns a case wherein the agents are infinite rational, whereas the other has to do with bounded rational agents. First, we suppose that the agents are infinite rational, namely they know the existence of the game while sharing the same decision-making mechanism. Thus, in light of infinite rationality, the target tracking problem can be thought of as a zero-sum game. In particular, V star is a value function, while U star, D star is an as-equilibrium, namely the saddle point policies. Unlike the previous analysis, now we relax the assumption of the perfect rationality and we consider that the agents are bounded rational. Thus, we shall develop a level K thinking model wherein each player operates under the belief that all of her opponents perform K-1 thinking steps. Consequently, the level K UAV's policy comes from solving the following optimal control problem. The next theory establishes that the policies converge to an as-equilibrium for higher levels as long as the following sufficient condition is satisfied. However, in our case, it is impossible to compute analytically the optimal policies together with the value function. Thus, we shall employ an adaptive learning-based framework. The critic neural network learns the value function, whereas the actor neural network learns the optimal strategies. Furthermore, a data-driven learning framework is introduced whereby the UAVs learn the target's level of intelligence. To validate the efficacy of the proposed approach, we carried out some simulations. This figure illustrates the target engagement. In particular, we observe that the pursuers circumnavigate the target while the target is evading them. Furthermore, while the pursuit is taking place, the UAVs are learning the profile of intelligence of the target. Thank you for your attention. And if you have any questions, then do not hesitate to reach out to me.
Hello, and welcome to my presentation about the development of a haptic device for inertial feedback. To go over a few basic terms, teleoperation is usually implemented in order to ensure stability at the remote site, and transparency and interaction essentially keeps operator inputs and disturbances at the remote site and allows them to be properly represented at the opposing site. Haptic feedback allows the operator's body to become part of the feedback loop. And then there's two main operational paradigms, precision, which is typically seen in like surgical robots, and then inertial, which is what we're targeting for this. The goal is to develop an inertial feedback ungrounded leader device for remote signals. For the inertial feedback approach, the main challenges are the bandwidth for signal magnitudes. Higher magnitudes require larger and larger actuators, and then the output rise time. The intended application being for robot graffiti painting, which has a lot of dynamic motions and requires more freedom of movement. We're going to be going with an ungrounded approach. And this does introduce a challenge with decoupling system signals from the inertia of the actual control device. But we're going to be going with a torque-based approach, which is visible here, where we have basically a dual flywheel system, dual reaction wheel system that is going to be actuated by a linear actuator to change the torque lever arm. The operation is going to be in terms of prioritizing when to actuate the linear actuator, when to activate the reaction wheels, and using our sensor data in order to properly represent the intended torque outputs. The benefits of the system are to reduce the mass to bandwidth ratio and then lower the signal magnitude's rise time. There's two main tests that are going to be used to evaluate the device. It is the sudden acceleration at the tip of a virtual lever to actually validate the bandwidth and rise time benefits of the system, and then a dynamic mass agitation, dynamic mass being something like a liquid, to simulate continuous changing signals where the user's agitation of the device is going to modify the expected outputs. Thank you very much.
On learning maneuvers with uncertain systems, where those uncertain systems have symmetry. So maneuvers are the core of a technique known as maneuver-based path planning, where you leverage symmetry in your dynamics to reuse control laws. If you look at the example system down here, the symmetry in this case is in the translation and heading space of the vehicle. And if you translate and rotate a vehicle by some amount, the trajectory that you're going to follow for any given maneuver is just translated and rotated by that same amount. So in maneuver-based path planning, their point is to be able to reuse these controllers. And so that reduces the cost of planning to just figuring out how to concatenate those maneuvers. And it even works if your system is uncertain. So they're nice techniques, but they have a big downside, which is that you need to have a nice library of maneuvers in order to get good concatenations. And so building these libraries by hand, that takes a long time. You need to have a domain expert, and you even then still often end up with low-quality libraries. This example library here has no maneuvers that do short, sharp turns. And on top of that, for uncertainty, it's important to make sure that every possible exit state of every maneuver is a state where you have additional maneuvers available or you're stuck. And so guaranteeing that is a non-trivial exercise. So we'd like to do better by using learning to discover maneuvers to fill in these gaps. So the first step then is to figure out where those gaps are. So to do that, we take an existing library. This library here is drawn from the uncertain library constructed for the model system. We're going to focus just on the nominal situation. And then you take this library and you evaluate the cost to go on the symmetry space. And all that tells you is that it's expensive to get to the goal from really far away. Not useful. What is useful is if you take a local difference kernel and sweep it, the output then is only large if it's more expensive to get to the goal from a point than it is from all points near that point. And so that tells you there's something wrong with your library for that kind of condition. So using this new weighted map as a suggestion distribution, we can train a soft actor critic to fly to the goal from initial conditions that we drew according to how hard they were. and we can reward this actor critic obviously for getting to the goal, and then also to reduce sparsity, give it a reward anytime it decreases the error to the goal. And so early on in the training, we see that it's got a decent idea of what it's supposed to be doing, but it's still underutilizing the control authority. It could turn much more sharply, and that would be better. So after some amount of training, you have a collection of trajectories that the actor critic has flown, and now you want to go through those trajectories, like this one here, and identify candidates, things that could be good maneuvers. So the first thing to do is to figure out what in this trajectory we've already seen. And so in this trajectory, the kind of initial part of the trajectory is all stuff that we all have already seen, so that's not new. But the latter part, we zoom in on that, extract it. So that's a segment of trajectory and a sequence of control inputs that will produce that trajectory. So we can use that as a reference trajectory inside a controller. So we run a direct collocation optimization to select controller gains to minimize the tracking error even under uncertainty. And so with this new controller output plus the reference trajectory and the reference controls, we now have an uncertain maneuver that we can add to the library. And hopefully that will result, if we run this thing again, we'd get a better, smoother local cost difference metric.
Hi, my name is Bharat. I'm in the robotics PhD program, and I'm studying real-time cell model parameter estimation to optimize HMSC growth. Human mesenchymal stromal cells, or HMSC, are stem cells that show promising therapeutic effects for regenerative medicine. Specifically, their immune suppressive and immunomodulatory functions are highly leveraged in clinical studies for various conditions. The problem is that we have a limited number of donor cells, so we need to grow or expand these HMSC for use in further clinical studies and therapies. And bioreactors are the platform that we use to mimic the conditions required for cell growth. There are many different types of bioreactors, but the one on the left is the one that we are using since it is enabled to automation, and it has multiple different flow loops that we can control for to replenish nutrients that the cells need to grow. In the prior work, we defined a control-centric model that accounted for these different flow loops and our different sensing limitations. And we also defined a cell production model that was quite naive because it assumed an exponential fixed growth, as well as a fixed glucose consumption and lactate production model, where glucose and lactate are the two main nutrients present in cell glycolysis, which is the metabolic pathway that cells use to grow. Now, we want to come up with a more complex model that captures the actual cell growth dynamics by not just counting the number of cells, but also differentiating between active and dead cells, where active cells are the ones that are actually able to double, and dead cells are dead. And we will track these different growth rates as a function of time. So we will have these as time-varying parameters instead of fixed parameters. We are going to leverage mass transfer equations for the nutrients because glucose and lactate are still the main indicators of cell growth and cell death. And we were also going to estimate the cell confluency or cell density. Since these cells grow in a monolayer, once the density gets high enough, the death rates will increase and will also limit the growth rates. This model is going to split cell growth in two different phases. The first phase is over the first 5 hours or so, where the cells attach to the fibers. And the second phase is where they grow in bulk over a multiple number of days. And then finally, we will track the number of viable cells, the number of dead cells, based off of our growth and death rates. With this updated cell model, we can use an extended Kalman filter to come up with noise optimal estimations for our different parameters and states. However, with nearly 250 extra states, especially added with this new model, the inverse to compute for the Kalman gain is computationally expensive and is also singular. So in order to ameliorate this problem, we're going to use multiple partial observers with only the relevant states included for each state that we actually want to observe. Finally, we have designed a novel hardware setup to gather our data with an incubator to provide the correct temperature and humidity requirements, as well as fluid tubing loops and bubble traps to make sure that bubbles that form in the loops due to evaporation don't go into the fiber cell.
Hi, I'm Moshe Ho, and I would like to present my work on belief space partitioning for symbolic motion planning. The background of my research is to solve the underwater vehicle navigation problem in the ocean flow field. And we would like to argue that this problem should be formulated as a POM-DP problem or a partially observable Markov decision process problem. The first reason is the ocean dynamics is highly uncertain. As you can see in this animation, the dynamics is highly complicated and there's no model that can perfectly predict this complicated dynamics in the future. And then the second reason is the partial state observation. When the vehicle is at surface, the position can be known by the GPS signal. But when the vehicle is underwater, the GPS is not accessible, and the vehicle has to use the acoustic methods to compute its location. But this kind of method can have high uncertainty in the observation. So we can only get partial observation on the state. So this is a POM-DP problem. And the general way to solve a POM-DP problem is to define the belief state as the posterior distribution of the system, conditioning on all the historical information of the system. And then we can consider the belief dynamics, which is the propagation of the posterior distribution, and consider this as the system dynamics. Then given the belief dynamics, we can design a planner to solve the planning problem. But the problem is this belief dynamics is an infinite dimensional mapping between the posterior distribution at each time step. So this does not have a closed form. So the first problem is we want to derive approximation model for this infinite dimensional belief dynamics. And then given the approximation model, the second problem is to solve the planning problem. The difficulty in doing so is when we consider modeling the belief dynamics, the first general problem is the curse of dimensionality. Because the belief dynamics is infinite dimensional, so the number of parameters required to describe the belief dynamics will grow exponentially as the system dimension increases. And then the second difficulty is the nonlinear dynamics and non-Gaussian noise. The most commonly used method to parameterize the belief dynamics is the Gaussian distribution parameterization. But this will not work well if we have nonlinear dynamics and non-Gaussian noise. So the contribution in my work is we propose a novel parameterization method to approximate the belief dynamics. That is a discretization strategy of the belief state that allocates a fixed number of partitions in regions that the vehicle will most likely to visit. And by doing so, we have this belief partition method that can significantly reduce the computational time required to solve the planning problem. Thank you. This is all in my presentation.